we have been discussing about the interaction of electromagnetic radiation with matter. Now, I hope that you are understanding what is electromagnetic radiation. So, I am presenting in front of you this figure of the electromagnetic spectrum. So, I told you that the electromagnetic radiation that we come across in our day to day life is a bundle of energy containing different frequencies. Now, in this figure I have here on the top left, on the left side, I have put the wavelengths. It starts from 10 raised to minus 6 nanometer and 10 raised to minus 5, minus 4, minus 3 like that, for I have listed them out, and then up to 10 raised to minus 1 nanometer it is here. 1 nanometer is 10 raised to minus 6 meters. So, after that I have started from 1, 10, 100, 100, 10 raised to 3 nanometer, 10 micrometer, etc. Here the scale changes. We do not call it nanometer anymore, but all are interconvertible. So, on the left side I have 10 micrometers now, 10, 100 and 1000, and then after that we are moving into millimeter range, that is 10 mm, 10 centimeter, 100 centimeters, and then afterwards moving down, still down I have 10, 100 and 1000 meters, that is then I have up to 10 kilometer, 100 kilometer, and then 1 million meters, 10 mm and 100 meters. So, on in the middle I have gamma rays, that is gamma rays range from 10 raised to minus 6 to 10 raised to minus 2 nanometers. Okay. The top 5 correspond to gamma rays. Below that I have X-rays. The wavelength range will be from 10 raised to minus 1 to 10 nanometers. So, part of the electromagnetic radiation is also composed of X-rays, and lower side I have ultraviolet rays, and then still you go down, you come across visible range, which is a very small portion of the total electromagnetic radiation spectrum. Then after the visible range I have near infrared, far infrared, and then microwave. So, microwave you are all very familiar with, ranging from 1000 micrometer to 1 meter, 100 centimeters. We use microwaves in our kitchen also. Ovens based on microwaves are available, and then radio waves, of course you would be familiar, because that is where you will be hearing lot of music and other things. They all contain they all range from 100 centimeter to 100 megameters. So, the whole electromagnetic radiation can be classified as gamma rays, X-rays, ultraviolet rays, visible light, near infrared, far infrared, microwave and radio waves. So, yesterday I have explained to you that gamma rays are all products of nuclear reactions, and they are nothing but basically neutrons which are being emitted, and X-rays are when electrons bombard on metals, X-rays are produced, and these are having slightly higher wavelength range than gamma rays. Ultraviolet range are still weaker in terms of energy and longer in terms of wavelength. So, next comes visible. Ultraviolet rays are all part of our sun's energy, which is supposed to contain vitamin D also, and then visible light. Visible light has several components: violet, indigo, blue, green, yellow, orange and red. and next to that we have near infrared, far infrared. Infrared lamps people use in day to day life for the operation of for sports persons. Whenever they get injured, infrared lamp is focused on the parts affected by the body, bruises etc. It is used as a painkiller. So, we are all very familiar with most of these radiations, except gamma rays. Maybe in, you may not come across day to day life, but X-rays, medicine, ultraviolet is used in this sunscreen lotions and things like that. Visible light, of course, I do not have to explain to you. Everywhere you see all around you visible light, near infrared and infrared, far infrared are used for sports persons treatments, and microwaves are used in the kitchens, radio waves for music and entertainment etc. And then again microwaves and radio waves are classified as UHF, VHF and HF etc. Ultra high frequency, very high frequency like that, and very low frequency, and below that we have audio, this thing. So, you can see that the electromagnetic radiation, the visible light, what we normally are exposed as human beings, it forms a very small portions of very small portion of the total infrared total electromagnetic radiation. And for our spectrophotometry, for this course we will be concentrating on ultraviolet and visible light and near infrared light also, radiation also to some extent. So, this is what we have been talking about. We will continue our discussion. Basically, how our knowledge of, to determine how our knowledge of spectroscopy has developed over a period of time. So, basically all can be traced to electronic structure of the atoms, and I have already explained to you that Sir J. Thomson's work about electrons and neutrons etc. Rutherford's modified theory also we have looked at it, and our next understanding of the spectroscopic techniques came from Bohr, Professor Niels Bohr, a Nobel laureate who proposed a radically different view of the atomic structure based on the optical spectrum of hydrogen. He included the postulates of quantum theory by Max Planck also. So, what essentially Bohr reported is that the electron in a hydrogen atom is always describes a fixed circular around the nucleus. That means, electron is going round and round the nucleus, that is the Bohr's model. So, such orbits are named as stationary orbit. Actually, what I want is I want you to understand that there is a nucleus like this, electron is going around. When the electron is excited to next higher energy level, its diameter would increase and it will be going at a still higher energy level. Again if you provide more energy, again it will describe a bigger path, but still going round and round the nucleus. You supply lot of energy, electron may go off, that means it will ionize. So, the orbits in which the electrons are moving around the nucleus are known as stationary states in Bohr's theory, and he thought of various circles differing in radius. The angular momentum of each stationary states was an integral multiple of nh by 2 pi, that is Planck's theory. What he said is, in quantum mechanical theory, when you supply certain amount of energy, electron goes to next higher energy state, but it has to be a definite quantity of energy corresponding to the energy difference between the final state and the lower state. Okay. So, in between suppose you supply energy, in between the two states it will have no effect. It will not excite the electron to neither higher energy level nor it will fall back. So, that is Planck's theory. So, in Planck's theory, the energy difference between the two states is given by nh by 2 pi, and the angular momentum of the electron, because we do not want the electron to fall back into the nucleus. So, it has to be balanced by the angular momentum, which will be exerting some sort of a centripetal force to keep it in circulation. So, that angular momentum is given by mvr is equal to nh by 2 pi, where n is an integer called as quantum number. I think you are all familiar with this, and he also postulated that as long as the electron remains in a given orbit, it neither radiates nor absorbs energy. So, that is the fundamental truth. So, when the electron moves from one orbit to another, it was considered to involve absorption or emission of energy. Okay. So, this energy manifests as radiation, and the frequency of such radiation is manifest as a spectral line, in which could be related to the energy of the electrons in the two states E1, E2 or E final or E initial, like that. What we are saying is there is a nucleus, electron is going round and round, I am going to supply energy, and when I supply the energy, electron will go to the next higher energy level. At that time, a certain amount of radiation is going to be either absorbed or emitted. If it falls from higher energy to level to lower energy level, the difference is emitted. So, if you take the total energy of the radiation before excitation and after excitation, there will be certain amount of energy difference between the two states, right. So, this energy difference is the spectroscopy. Okay. So, the energy difference I can put a photographic plate. So, as the electron moves from one to higher energy level, if I put a photographic plate, there will be certain amount of signal corresponding to the two different energy states. If the electron is occupied, there will be occupied signal. If it is not there, if it is excited, then there will be certain amount of light will be emitted or excited or absorbed, which can be measured. So, each transition is always accompanied by certain amount of spectroscopic evidence, which manifests itself as a sharp line on the photographic plate, and the and in the energy level spectrum diagram also, energy of the incoming radiation. So, if you take hydrogen, supply certain amount of energy, electron will be excited to next higher energy. So, there will be one signal, and then suppose you excite it to next higher energy level, there will be second signal. So, suppose there are number of electrons at the same energy level, all of them going from the same energy level to next higher energy level, there will be certain amount of transitions. These transitions, suppose the electron is at the ground on the first step. Imagine a very simple analogy is, imagine a number of stairs from ground floor to third floor or fifth floor. So, first floor there will be a platform, second floor there will be another platform, third floor will be another platform. Now, some electrons are at the ground floor, you take imagine a football and kick it to the first floor. Okay. That energy difference, the moment it hits the first floor, you are going to get a signal. So, sometimes you may hit the second floor. So, what happens? You will get a second signal for the same electron. Instead of hitting it to the first floor, you will get the second signal for the same electron. Suppose you send it to third floor, the again energy difference will be much more, and third signal comes. Now, that is one type of signal. Now, imagine you are not on the ground floor, but you are on the first floor. From the first floor, you can send it to second floor and third floor, that energy difference also will be there. So, for a given element, number of spectral signals will result if depending upon where the electrons are before you supply the electromagnetic radiation. Some are on the ground floor, some are on the first floor, some are on the second floor, like that. There will be a series of lines corresponding to each energy transitions. These are known as the line spectrum. So, the line spectrum of a hydrogen have been defined and recorded since 1700 AD in different series corresponding to, they have been grouped. For hydrogen, it is line spectrum is given as Lyman series. Here what happens? All the electrons are in the ground floor, that is n is equal to 1. From n is equal to 1, the electron may be transferred to n is equal to 2, n is equal to 3, n is equal to 4, like that. So, all the lines originating from n is equal to 1 are known as Lyman series. Okay. Now, imagine some electrons are on the second floor, n is equal to 2. From n is equal to 2, I can excite the electron only to 3, 4, 5, etc. So, all the electronic transitions or spectral lines originating from n is equal to 2 to different energy levels are known as Balmer series. Okay. Similarly, n is equal to 3 is known as Paschen series, and then n is equal to 4 would be Brackett series, and then n is equal to 5 would be Fund series, like that. But as you go from higher to higher energy levels, from n is equal to 1 to 2, the energy level would be very high, 1 is to 4 would be still higher, but 2 to 3 and 2 to 3 to 4 or 4 to 5, the energy difference between these energy levels would be much lower. So, the Bohr's theory could explain the spectra of origin, how the different kinds of lines are obtained by the same element, but it failed completely when applied to multiple electron systems. So, this is the one of the greatest tragedies, that it could not be applied, therefore, it had to be modified, and which took place down the line after some time. Further, it could not account for the splitting of optical lines. For example, if you see the same light subjected to magnetic field, instead of one single spectral line, you will see two spectral lines, one without magnetic field, one signal, with magnetic field you will get two signals, same line, it splits into two. So, Bohr theory could not account for such changes at all. Therefore, the Bohr model, even though basically it was correct, it could not explain all the spectrographic changes. It could not account for all the spectrographic changes that take place. It was slightly more. The same concept what I had told you, I had drawn it here. Here you can see this is the hydrogen atom, here n is equal to 1, the first circle, first half circle is n is equal to 1, second half circle is n is equal to 2, 3, 4, 5, 6, 7, like that, and all the transitions taking place from different energy levels to 1 are known as Lyman series. So, here the transitions occurring from different energy levels, but ending up only at n is equal to 2 is known as Balmer series. Third is Paschen, that is n is equal to 3, n is equal to 4 is Brackett, n is equal to 5 would be Fund series. So, the same element hydrogen can show 5 different kinds of line spectra which can be accounted. So, because of the failure of Bohr model, what happened is down the line Sommerfeld modified Bohr's theory to include elliptical orbitals. Bohr's theory said it include all the stationary states are circular, whereas in Sommerfeld theory he said it could be elliptical also, but as a special case it can be circular, just like in hydrogen. So, the velocity of an electron moving in such an orbit would be greatest when it approaches closest to the nucleus and least when it is the farthest. This is a very simple assumption that imagine planet Earth going round and round the sun, but when it is nearest to the sun, the speed will be very high, and when it is farthest the speed would be very slow. So, this introduces the variability in the orbit also, which as a whole will precess around the nucleus, and this precessional movement will result in small energy changes, which will be reflected as fine structure in the spectrum. That is, I explained to you that it is a magnetic field that makes it look somewhat more complicated. Instead of one single line, it is double line. So, such fine structure could be explained by Sommerfeld's theory. So, what he did essentially was he permitted the subdivision of the Bohr stationary states of slightly differing energy levels corresponding to the differences in orbit shapes, and this is the basis of modern concept of electronic configuration also. Further, it projected the possibility of penetrating orbits. That means, if imagine an orbit like this in a round space, and I can bring another orbit with an electrical magnetic field, but they can be overlapping each other. If I imagine the orbits are rigid, then there is no overlapping, they can be only come nearer each other only up to a certain extent. But if I have an overlapping orbit, there could be certain amount of overlapping, it could be 10%, 15%, 50%, 50%, 100% like that. The one orbit can overlap the other orbit. So, the certain electrons may penetrate closer to nucleus than others, in thus permitting qualitative pictures of the more complicated atoms. Okay. So, what we are essentially saying is we can summarize the Sommerfeld's theory also. In general, inert gas atoms with the exception of helium contain 8 electrons in their outermost orbit, and helium, neon, argon are all having 2, 10, 18, 36 etc. I am teaching you high school chemistry again. They have so many number of electrons and represent the end of various horizontal series of periodic classification. And then they said C.R. Berry postulated that maximum number of electrons in a various shells are 2n square, that is 2, 18, 2, 8, 18 and 32. These are the maximum number of electrons that can be in a any shell. So, no shell can contain more than electrons unless more than 8 electrons, unless another shell further removed from the nucleus is being formed. This concept permitted logical explanation for the configuration of the transition and inner transition elements. What they, if you study periodic table, you will see that many of these penetrating orbitals etc. will be there, and they all go to the added electron with higher increasing number of increasing atomic number. With the electron nuclear mass will increase, but the electron will go into an inner orbital, not the outer orbital. So, the actual size of the element shrinks, it does not expand with added electron. So, it is the beauty of the periodic table. If you study that, you will be knowing. So, if I have to plot electronic configuration of inert atoms, it should be like this: helium, neon, argon, krypton etc. Here you can see maximum number, atomic number would be 2, 10, 18, 36, 54 and 86, that is 2n square rule, and the K shell will always have 2, L shell will have 8, M shell will have 8. The outer electrons are always 8 except the exception of helium, and inner could be 18, 18, 18 and 32. So, this is a very fundamental electronic configuration of the atoms. which we all know, and the quantum now having known the structure of the atom and a little bit about the periodic table, what we want to say is the concept of electrons revolving around the nucleus, atomic nuclei, is limited to well defined shapes, and it is essentially rough pictorial presentation. You must always remember that in electronic compositions, in electronic representation of the orbits and orbitals, etc., there are no exact figures. There will always be certain amount of distortions and other things, depending upon how mathematically correct you could be in incorporating the basic conditions of the transitions. So, modern based on wave mechanics depict comparative density of the electronic charges at any given point within the atom based on the theory of probability. So, essentially what this means is that electrons will tend to group themselves in a series of positions relative to the nucleus, which may be considered as energy levels. We have been talking about energy levels since quite a long time, and these energy levels with respect to the nucleus, the transitions are permitted only between the energy levels which give rise to spectrum. That is the beauty now. Now, what we are saying is any transition that happens in a given molecule must give rise to spectrum, otherwise it is not permitted. Quantum mechanically it is not permitted. It has to be some sort of NH by 2 pi, that formula it must maintain. So, the electrons are basically best described in terms of 4 quantum numbers again. So, one is principal quantum number n, another is orbital quantum number, another is magnetic quantum number, and fourth is spin quantum number. So, the corresponding energy levels are given by this equation. I will not go into details about the derivation of these equations, which are fairly well described in a lot of textbooks, but it has not much relevance to what we are going to study in this MOSC course. Okay. So, but for our practical purposes, the orbital, we can say that the orbital quantum number is a measure of the orbital angular momentum that is given by h into the square root of L into L plus 1 divided by 2 pi. Similarly, I can describe the spin quantum number also, and magnetic quantum number also, and magnetic quantum number will come into play only if we have a magnetic field, and if this normally in magnetic field spectral lines split, and that is known as Zeeman effect. And this Zeeman effect is also very part of our spectroscopic techniques, which are very important, which takes place in the atomic absorption spectrometry. That we are not dealing here right now. We are dealing only with the molecular spectroscopy, but Zeeman effect we should all be very familiar with respect to the splitting of the spectral lines in magnetic field. So, the magnetic quantum numbers change from 0, the L is equal to 0, L is equal to 1 means there will be 3 magnetic fields, minus 1 plus 0 and plus 1, like that. So, different magnetic splitting will take place, and the spin quantum number, spin of the electron also can change, that is given by this expression h into square root of s into s plus 1 divided by 2 pi, but the spin quantum number can have only 2 values, that is plus half and minus half. So, without going into details, we just have to confirm now that in any orbital there can be only 2 electrons within any atom, that has all, that means all the 4 quantum numbers cannot describe single electron or 2 electrons. No 2 electrons will have identical 4 quantum numbers. That is what it means finally. It is just like having a rupee note which is different, which is similar in all aspects except the numbers. So, similarly every electron has an address containing n, l, m and s quantum numbers. So, knowledge of the exact order in which electrons atomic orbitals are occupied is based on the interpretation of atomic spectra only. So, our knowledge of comes only from atomic spectra in terms of how spectral lines result from the permitted electronic transitions. So, heavier atoms will have definitely more number of electrons, more number of orbitals, more overlapping. So, the spectrum would be more complicated than simple atoms like hydrogen. So, here is a practical representation of atomic orbitals, and here S orbital you can see on the left side, that is fairly spherical, and the p orbitals are distributed above the bond axis, and the bond the black line in between the two represents the x and y axis, and you can see that p orbitals are dumbbell shaped, placed above and below. Along the axis there is no electronic density, not much electronic density, but electronic density is spread evenly on the above and below the x axis. Similarly, there will be number of d orbita, there are 3 p orbitals, because one would be in along xy direction, another will be in perpendicular direction, another could be vertical direction. So, the d orbitals are further splittings from the pi orbitals. For your imagination, you can say that the electrons are the orbitals are something like this, and again there will be 5 different d electrons, and similarly there will be number of 7 f orbitals. So, these are the colored areas represent the maximum concentration of the electrons cloud in the space represented there. So, here you can see px orbital is one along x direction, one along y direction and one along z direction. So, there could be always 3 pi orbitals, and the energy levels of d again they will be in different shapes, but they could be represented something like this 1s, 2s, 2p etc. This I have already shown you in a crude form earlier, and the energy level diagram for atomic orbitals can also be represented something like this. This is also a very similar very famous pictorial presentation of the filling of electrons in a periodic table. Okay. Now, the periodic table as we understand as of now is a modern periodic table based on atomic number, and I think you are all very familiar with this. Hydrogen here and helium here, that is the first row, and 2 electrons, and then lithium, sodium, potassium, cesium etc. These are all alkali metals, and then alkaline earth metals, transition metals, and then coinage metals, zinc, cadmium and mercury, palladium, copper, nickel etc. coinage materials, and these are lanthanides, cerium 2, lutetium are lanthanides, and here I have the semi metals, metalloids, silicon, phosphorus, sulfur, gallium etc. I have halogens here, fluoride, chloride, bromide etc. These are all very simple familiar things for you to know. So, based on the previous discussion, we know about periodic table, we know the interaction electrons electronic filling, we know that the electrons are all around the nucleus occupying different energy levels, and we also know that the energy levels can be changed, that is the occupation of the electronic orbitals and molecular orbitals can be changed by the supply of electromagnetic radiation, and this electromagnetic radiation, whenever it effects a change according to the quantum mechanical rules, represents a spectral line. So, this is what essentially we have been driving at, and we will continue our discussion on the interaction of electromagnetic radiation with the matter in the next class. That is, we will discuss a little about reflection, refraction, etc., and then we proceed on to the spectroscopic technique of the electromagnetic radiation, that is spectrophotometry, how it works. So, based on the electromagnetic we will also look at what are the different kinds of transitions possible in electromagnetic radiation, how we can predict where a spectral peak can be calculated without doing the experiment. Okay. So, that forms the fundamental basis of spectrophotometry. So, thank you very much. Have a nice evening.